whole idea. It says that basically the more you try and pin down an object's position, the less you know its momentum, which is its mass times its velocity. The more you try and pin down its mass times its velocity, its momentum, the less you know its position. Okay? Now that doesn't turn out to be a big deal for objects on the large scale, like in the size of things that we see. When you get down to the size of electrons and protons and stuff like that, it's a really big deal. And we did it for what? A proton, and we said the uncertainty position is probably like 10,000 times the size of the diameter of the proton, which is a problem. It means we don't know where it is within 10,000 diameters. Either way, that's kind of crazy. It's like, what if I couldn't tell where you are 10,000 times the width of your body? Now imagine that shape going out from you, 10,000 bodies going out in all directions, and then be like, I don't know where you are. So that was Heisenberg's uncertainty principle. And it basically comes down to the fact that really, really small things are impacted by the electromagnetic radiation that's everywhere. So it's kind of hard to pin things down because they're moving as a result of being impinged with this energy. Okay. Then we started talking about quantum numbers. And when I started talking about them, it looked like everybody got me. But by the end, I started seeing people looking very confused. Is that probably right?
Yeah.
Okay, and that's exactly what I expected, right? I said, don't be surprised if you walk out of here today not knowing what we're talking about. Okay, so what we're talking about is this. It's hard to know where an electron is and where it's going because of Heisenberg's uncertainty principle. So we looked at a computer program that showed where electrons were at specific points in time. Do you remember that with all the dots? And if you go to those pages I referred you to yesterday in your book, they have the picture of those same charts with the little dots. Okay. And so what happens when we still start looking where an electron and we say, where are you now, where are you now, where are you now, where are you now, we find it could be a lot of different places. But if we narrow it down to 90% of the time, we can get a pretty tight, concise space around the nucleus of where a particular electron may be at a particular time. If I try to do it 100% of the time, then I have to say the universe. That's the shape. Okay, it's just too big. But just narrowing it down 10% down to 90% of the time, I start to get a real shape. And those shapes are things like spheres, like bilobes. Okay. So we get spheres. Tiny little sphere there. We get shapes that are like bilobed, and actually I'm going to get them all out. Oh, bring out all my toys for you. So, one of the shapes, the simplest shape we get is a sphere. And we call that shape S, okay? And you get them at the first energy level, n equals 1. Rho equals 0 to n minus 1. So rho equals, in the first energy level, 0 to 1 minus 1, or 0, which means, Jarrell, you have to wake up. You got to wake up or you're going to leave. Okay? You're like passing out. It's concerning. So get your hand off your chin. All right? Get ready to take notes. Pay attention. All right? We good? All right, Joe. Do you want to do jumping jacks or something? Is that going to help? You want to do jumping jacks?
I just like standing back.
Yeah. That actually, if that'll get you awake, that's fine. Get fresh air or something like that. Okay. So the simplest shape we get is sphere. We get it at the first energy level, where n equals 1, rho equals 0 to n minus 1, or rho equals 0, which means S. 0 means S, sphere. At the second energy level, n equals 2, so rho, shape, equals 0 to 2 minus 1, or 0 to 1, which means I get S's, that's 0 for m sub rho, and I get P's, which are bilobes. That's rho equals 1. You with me? You losing me? I'm losing you? Okay. So energy level is n. Everybody good with that? N dictates what shapes you can have. So at the first energy level, rho is the shapes that you can have. And that range is 0 to n minus 1. So if at the first energy level, all I can have is a row of 0. Okay? Which we correlate to S, sphere. When I get to the second energy level, rho now equals two numbers, 0 and 1, which means S and P. Which means I get another sphere, but that sphere is bigger than the first sphere. Because n tells you the size and the energy. Energy level tells you size and energy. But then when I get to row of 1, that's P. Now I'm pulling out three shapes. I'm pulling out, this is a PZ, pointing at you. This is a PX on the x-axis. This is a PY on the y-axis. Okay. Now the reason that I only get one S, single S at any energy level, but I get three P's, is because it's orientation. Rho, n equals 1, rho equals 0. That's S, right? N equals 1, rho equals 0. That's S. M sub rho, orientation, is plus or minus rho. So if rho is 0, it's plus or minus 0. It's 0. You get one shape for S, 0, for M sub rho. There's only one way to place a sphere at the center of an XYZ coordinate system, and it's at the center. But for P, rho is 1. We don't get that to energy level 2 because we get n equals 2, rho equals 0 to 2 minus 1, or 0 and 1. So at the second energy level, I get S, 0, and I get P, 1 for rho. Orientation is plus or minus rho. So for the S, it's 0. For the P, which is a row of 1, it's negative 1, 0, and 1, which are P sub x, P sub y, P sub z.
On a graph, can you have all three of those?
Yep. That's exactly what's going on. Yep.
Is P2 just not on a y or x axis? It's just somewhere position between it.
P
Says P.
Z,
Oh, that's a
P Z, yes.
So wouldn't all of those at once be this? Or do they not mesh?
Yeah, they would superimpose on top of each other. So if you want to think about them superimposed, you can think about all the P's look like this when they're all filled up. Are you with me so far? All right, energy level 3. Hopefully you're starting to see the pattern here. Energy level 3, n equals 3. So rho equals 0, 1, or 2. Yep.
So at energy level 3,
Yep.
would it have row, like the shapes for row 0, 1, and 2?
Yep.
So it would have S, P, and D in it?
Exactly. Every energy level, you keep picking up a new shape. And when you add a new shape, there's always two more shapes that's being added. So it's 1, 3, 5, and then 7. So for third energy level, right? So n equals 3. So rho is 0 to this minus 1, or 2. So I have 0, 1, and 2. I have S. I have my P's, which is 3 orientations, because in negative 1, 0, and 1, plus or minus the number. And I have 5 D's. There's a clover leaf. That one's lying along the plane of the, what would that be, the X and the Y? Or,
Yeah, that's the X
plane.
and the Y.
Yeah. So they're lying on different planes. Any which way. This one's twisted 90 degrees to it. This one's more up and down, and this one's more up and down. They're twisted 90 degrees to each other. And then you got this oddball that looks to me like a glazed donut stuffed through a regular donut. Glazed twist through a regular donut. So somebody described it to me that one year. One of my students said it. I was like, that's a good description. I'm going to keep that. Okay. So, question.
Yeah, but you said that they're, for every energy level you go up, you get a new shape.
Yep.
And you said for every shape that you get the two.
You get two more shapes. So you get one S, right? But then you got two more 3 P's, and then you get two more 5 D's, and you get two more, you get 7 P's, or 7 F's.
Oh, okay.
And I don't have an F model, sorry.
So, like, why is it important that we know what shape it is, and like when they get, like how big, like that's the max they can be, the all pink one over there? That's the max they can
No. This is something different. I'm gonna get away from those for a second. Why do we gotta know the shape? Well, one thing is the shape tells us something about energy. Okay, if you play with the spring and you vibrate a spring just up and down like this, it's pretty unenergetic. But if you start rippling it more and more shorter waves, it gets more and more energy. So we're trying to figure out how much energy these electrons have. That's one thing. And as far as the filling up thing, basically what we're going to do is we're going to fill a shape, and then once that's filled, we're going to move on to the next shape in the sequence, and I'll show you the sequence today.
So does what you said with the string stand for, like, no matter how big the wave is? Because, like, if you have just one wave in the whole length that you're putting it, but it's, like, super high, like you whip it, wouldn't that have more energy than just...
Yes. You're talking about amplitude. The best thing I can say is it's not an issue with these, okay? Because they're waving all at the same amplitude. If they're going to change energy, they change frequency. Because the amplitude, I'm sure, would have something to do with the attraction between the nucleus and the electron. That probably is going to control how much it can potentially wave. That's a guess. Okay. Yep.
Do shapes ever reach like energy levels?
Absolutely. So every energy level you get an S. You just get bigger S's as you go up. Every energy after from 2 and on you get a P. Every energy level from 3 and on you get a D.
Interesting.
Yep. Yep.
Will you ever get to like an energy level so high that it's just like the same shape as like an energy level lower, just bigger?
Well,
Or will it always like change shape?
well, no. I mean, what you're doing is you're retaining all the shapes that you had prior, and each time you go up an energy level, you're gaining a new shape. So yeah, at higher energy levels, you're going to have shapes just like the lower energy levels. The only difference is they're going to be bigger.
Although there are only so many shapes, right?
Well, no, there's an infinity. But the thing is, though, is once we get up to about F,
They just-
we've described everything on the periodic table in ground state. Now, when things get excited, then they can go to higher and higher and higher energy levels. So actually, those are good questions, actually. So it means that you're kind of thinking about all this. All right, so let me get what you got to get today. So here, your fourth quantum number is called electron spin. Electron spin. Electron spin quantum number. And that is denoted by M sub S. And this describes the spin of an electron. Actually, you might not think of electrons as having spin. That's kind of a weird thing to think about. But the problem, well, not the problem, but the thing is that when scientists look, and I don't know how they see this, but I know they see it. When they look at electrons, what they see is that electrons exhibit something called angular momentum. Okay, I got a little lazy Susan table here. Okay. Angular momentum is one of those things that kind of helps you stay up on your bicycle while the wheels are spinning. Okay, so a force in one direction, like the tire is spinning, help regulate another force. And so what we see about electrons is they exhibit this. And you notice when something shows it's an angular momentum, it's like I can take and rotate in this direction, but you notice that I'm spinning in another direction as I spin here. That's a result of angular momentum, okay? And we can see that. And we see electrons exhibit that when they're by themselves, okay? Now what we don't see is when two electrons are together, we don't see that angular momentum magnified. Now I don't know if you can see I'm spinning further every time this time. Oops, I'm about to fall over. What we see when electrons are paired up is we see no angular momentum because they're canceling each other out. Okay? So electrons are exhibiting spin. So then the question becomes, in which direction? Oh, I can't do it. Can you get it for me, Ben? I usually put it so I can reach it, but not today. This is my globe that used to be used. My upstairs hallway was a long straight hallway to bowl down bowling pins that my parents won as little trophies. And so that's why there's a big divot in the Pacific Ocean. And it's got the Union of Soviet Socialist Republics here, and it's got Yugoslavia, and it's got a lot of crazy stuff. Anyway. Spinning, right? Which way is it spinning? Counterclockwise, right? Everybody see that? Magic.
Clockwise.
Okay, so what's the point?
Based on your view.
It's based on your perspective, exactly. And so, since like what's up to an atom? You know what I mean? What's up to an atom? Who knows? You know, there is no up. So what we just do is we agree to call the first one number, and the second one another number, and we usually favor positive numbers. So the first electron we usually call +1/2, and the second one we call -1/2. So it can be plus or minus 1/2. Okay. And when you have all 4 quantum numbers, what you've just done is you've just described a specific electron in an atom. You've described its wave form, its wave function to that particular electron. And we're going to mess with those numbers as we go, okay? All right, so let's check this out. Here's a nice little tool here. It's called the orbital filling diagram. This is a neat thing that somebody figured out at some point, and it just works. So we're going to learn to construct this. And the way you construct this is you start out with 1s. So that's first energy level, sphere, which means rho equals 0. Very good that?
It's 1s, you said?
That's 1s. So this is, you're going to start at 1s, where this right here is n, and this right here is rho equals 0. And I'm going to number down 2s all the way down to 7s, because that's going to get us the whole periodic table covered. 4s, 5s, 6s, 7s. Then I'm going to start with p's, but when do we pick up p? What energy level? You don't get it till the second energy level, because you only get one new shape each energy level. So I'm going to start at 2p and go down to 7p. And guess what shape we pick up next? D, and you pick that up at the third energy level. I'm going to stop at 6D. If you want to keep going, be my guest. You just won't need it on the periodic table. So I stop short. And then we pick up F at energy level 4. And if you want to stop at 5F, you can stop, because that's all you're going to probably need. But you could keep on going. And in fact, both of these things go on for infinity. So this would go 7s to infinity s. This would go all to infinities, but each time you'd be picking up a new shape as you move out. Okay. Okay. You guys play some Chutes and Ladders when you were a kid? Chutes and Ladders, right? Little board game. You'd spin a dial or something. You'd go move along. If you landed on a ladder, you'd climb up. And if you were on a chute, you'd slide back down. Okay. So what we're going to do is go start here. Start at 1s. And we're going to go down a chute. That means 1s fills first. Then we're going to reset and go through 2s. So the first 2 diagonal arrows each go through one subshell is what it is. The next 2 arrows go through 2 each, again on a diagonal. The next 2 go through 3 each. The next 2 would go through 4 each if I bothered to write 8s, which I didn't, because 8s would be down here. And basically, this gives you the order that electrons fill. Oops. This gives the order subshells fill. Okay, now, although what I wanted to get done was just a tiny bit more, I'm not gonna get to it. I'm gonna give you the stuff you need to answer those tomorrow, but I'll tell you what, still try the homework, because you should still be able to reason through some of it. If you reason through it without the notes, you're gonna be in much better shape anyhow.